Hi there, everybody. This lesson, we're going to keep looking at dt to vt graphs. We're going to look at how to draw the vt graphs, which will allow us to see how you'd be able to determine what type of accelerated motion you end up with. And we'll just talk some more about each of the graphs and the forms, and so average velocity versus average speed, things like that. Lots of little details yet to focus on. So average velocity, we've seen before, where it's the overall displacement divided by the overall time, and so the overall displacement would just be the final minus initial, like this delta d here would be equal to, I'll make that be a vector, and it'd be d2 minus d1, and then the time, of course, would be t2 minus t1, and so on. And so your average velocity would be a vector just based on the overall change, right? So the actual displacement vector would be this. Right? So I think I said to show that on there, but yeah. So our units, if you're looking at meters per second, right, it makes sense because we have meters and seconds as our units there. What else do I want to have talk about here? Obviously, you can convert to different units as well and so on. But anyways, just to remind you that average velocity, the idea of it, versus if we're looking for average speed, a little example here of my home high school to Kingston. Google says it's about 56.2 kilometers, right? So if we were calculating the average speed, then instead of being velocity and displacement and so on, it's going to be speed and distance traveled, right? So just notice that this now, if we're looking at average speed, we're looking at the scalar version of things. And so this is just distance traveled. And we could even add on like along the path. Overall time, obvious that's not changing in any case, but yeah, this would be your speed. Right, no direction involved. Yeah, so pretty easy calculations to make here. The Google says it's 56.2 kilometers, and we're dividing by the 44 minutes that it says it's going to take, and just get a number, right? So the 56.2 divided by 44 ends up being 76.6 kilometers per hour. Okay, so you're getting that value. That's your speed. There's no, that's just the average speed. Now I want to just start to think about the motion as we go from one location to another, and what your distance time graph might look like. So if this was Rideau, then this is Kingston. Obviously, we're going to start at Rideau and we're going to end up in Kingston on this trip, right? If you traveled at a constant rate the whole way, you just exactly in a straight direction, and just at a constant rate, it'd be just like that. But obviously, that's not the case, and so you might speed up for a while. Maybe then you're traveling at constant speed for a while, and maybe you speed a little faster or a little slower. Maybe you stop for a little while, and then maybe you keep going, and eventually you get to that new spot. Now, I shouldn't have anchored myself into getting there in a certain amount of time, right? So let me just get rid of that dotted line. But basically, I should have said Kingston is here, and Rideau was there. Just basically whenever you get there, right? And so that's coming to a stop there, and so on. Like you picture there's details here where there was construction for a little while, and so maybe you're stopped for construction. Right. So if we're looking at that, that's your path along the way. If you're looking at saying, okay, well, what would this look like if you wanted to look at the overall average velocity? Because obviously the length of this path right here, delta d, the length of the path, led to speed equals distance over time. Versus if we did the displacement vector, let's do purple for displacement here. That's a little too thick, blocking everything out here. Go down to a thinner line, but I'll show And we got the displacement vector based on that as well, right? So yeah, so the velocity, your average velocity, right, would be that displacement over time. So hopefully I'm just giving enough examples and time to think about this that it's making sense and seeming pretty easy at this point. All right. If we were to continue with this a bit, we could talk about, Elgin being the initial position, so literally D1 or initial position, and then final position D2. And so those two vectors point, where you were and where you ended up. And so we've seen this before where we think of displacement as final minus initial, and quite literally what you're seeing there is the tail to tail vector subtraction diagram that we've seen in the course before, right? So from there to there would be your displacement. So on this graph, it's directed, obviously, the actual directions and so on. The previous graph was just showing values, right? But yeah, so displacement vector there. And then, like I said, it's your tail subtraction, and then you get the average velocity from that, right? So the actual path length along the way said there was 56.2, approximately the same locations. The straight line is only 47.80, and so that's really representing your displacement vector, 47.80. And of course, the path along the way is longer because of all the turns and twists in the road, right? So a lot of people correctly said, the one about your path to school, what would have to be true for your path traveled length, your distance, to be the same as your displacement. And people said I'd have to be like a perfectly straight path from home to school, right? So there's your displacement. So it's looking good. All right, so moving on from that a little bit here, just some more examples to go through here. Determine and illustrate on the graph the average velocity over the following intervals from 0 to 1.5, and then from 0 to 3, and from 1 to 2. So let's do red, so 0 to 1.5. So average velocity is just displacement over time, right? So overall displacement ends up being 50. It went out to 100, but then back. And so this is A. Red, 0 out to 3. So let's do 0 out to 3 and maybe purple. 3, right? So that's B. Not going to put the triangle in because it's going to get way too many lines. And then 1 to 2. Let's do orange and 1 to 2. So 1 to 2. Okay, so that's C. Orange. Okay, those lines are showing the displacements, and then the average velocity, of course, would just be the displacement divided by time, right? And so if you're looking at those values, in this case, your position, final position minus initial position, they're the same, so it's just 0. So compare the results from A, B, and C, and so on, which would be a most appropriate indicator of how fast a person was going. The average speed or the average velocity. So cars travel with the car is traveling with a constant speed. Turns around, but goes backwards and so on, but then forward and so on. So the speed itself all along is, pretty much this slope here. So I guess the one that's closest to that would be the purple one, right? Just in this case, but it doesn't really matter. It's just a question to show the idea of it. And then these other ones are very misleading, right? This stopped velocity doesn't mean anything in the context of this at all. It was literally going a certain speed the whole time, right? So slightly more realistic version of this kind of thing. Picture what this graph means, right? This is to go back to the lesson where there was a bunch of DT and VT graphs and we're trying to interpret what they mean. This would mean going forward at 100 divided by 1, so it's 100 kilometers per hour, right? This section, 100 kilometers per hour. And then boom, all of a sudden it's going 100 kilometers per hour the other way. And then boom, all of a sudden it's going 100 kilometers per hour forward again. That would be a rough ride, right? So a way more realistic version of that would be to smooth that out and give it some time to change those velocities. And it could be something along the lines like this where you slow down to a stop and so on, right? just have these curved edges. But we often don't show the curves because the details in the curves are tricky, right? So just be aware of that when you're seeing diagrams. There's some unrealisticness in them that's kind of accepted and pretty commonly done. It's pretty commonly done that way. Just a quick bit on this. So I note to myself here, I'm just showing this to introduce the idea of limits, which is a preview for grade 12 math and calculus and so on. So we have a position time graph, and so you should be able to interpret the motion here, like, you know, traveling at a relatively constant rate and then slowing down and turning around the other way, going faster and faster, and then turning the other way, you know, slowing down to a stop briefly, and so on, right? We should be able to visualize all of that. What I want to do is I want to look at the straight line paths, displacements, basically connecting 5 to 11 and so on. Okay, so the 5 to 11 time frame is what, from the 5 seconds, so right there, to the 11, be up here. I don't have enough page showing. Here we go, to the 11. So that's, you know, the displacement, and, you know, you can calculate the velocity, average velocity over that time interval based on that displacement we're seeing. And then let's go from the 6 to the 6-second mark to the 10-second mark. Make sure I have things here. So 6-second mark to the 10-second mark. So over that interval, it's a faster average velocity. 7 to the 9. There's 7 ish right there, and over to 9, which would be up here. Faster in that interval. 7.5 to 8.5. So split the difference here from there to there. And then finally, you know, 7.8 to 8.2, basically trying to go from there to there. And you can't even see it right now, but I'm going to extend that line. Think of it as crossing at 7.8 and 8.2. Might be something like that, maybe. So what we're getting is these intervals that gradually are approaching. I think this one was drawn a little bit wrong here, but basically gradually approaching the value that it's at. And it's, yeah. So the idea of this is that we end up with this tangent slope. And so that's a big part of the grade 12 math class, you know, advanced functions, and then it leads to even differential calculus, right? And so the idea of this one being, move it here, drawing on the page instead by accident, give me a sec. So that one being, this one here being like 8 point, or whatever it was, 7.8 to 8.2. And then if I get that same curve, you know, put it just as touching the surface there, it's your tangent, right? So basically this is representing the instantaneous velocity, or that velocity at that instant. Or maybe I'll change the color of that one and describe in blue. Let's do. And so this one here is your instantaneous instantaneous velocity at the 8.0 second mark. So it's it's just that velocity at a given instant, right? At that instant, I guess I could say. So eventually, in calculus, you'll have like an equation here. So it's like the position as a function of time, right? And then in order to get that value, you're going to be looking at the derivative, it's called, and there's a mathematical process that can actually give that slope value. And so we know the slope equals the average velocity. So I'll just do the average there. And so, as usual in math, there's a way to understand and see things visually. So the idea of the tangents or slopes, you know, becoming closer and closer to being the slope at that instant. And then you can use math processes to get the answer in a more abstract way. So it's kind of like looking at an area of a rectangle and counting the number of tiles versus, you know, the abstract way would be like length times width. Did a terrible job drawing the tiles, but you get the idea, right? So the math to do with it is calculus. Okay, so this value, slopes, great, but really calculus can give you that number, and that was Newton's baby. Basically invented a branch of math that to solve a situation that he was trying to work with, which was things that are changing. And so just remember here too, we talked about constant velocity dt graphs and the corresponding vt graphs. So both of those should represent constant velocity easily when you're looking at it to you. From a previous version of the class, when we did it in person, we ended up with 50 kilometers per hour. And if you look at the slope here, the slope of that line is like 13.145, and 13.145 times that 3.6 number that you'll become more and more familiar with for converting from meters per second to kilometers per hour gives you very close to that 50 mark. That was a really good result that year. So just more review of things. What if, so if we had the situation where the ramp was getting more and more steep, so we know this would be the situation if we had a ramp at a certain steepness, we'd have, sorry, I'm thinking of something different here. So yeah, this is totally different. This is different here. So this is now a new situation where we have a ramp getting more and more steep. I should have had another slide in here. I'll just make it on the fly quick here, where if we had a ramp at a certain steepness, so ramp at certain angle, right? And then in which case the graph isn't here for this one. So I'll just cross that one out or whatever and show basically that we would have this kind of a graph, right? We'd have that as the result. That one's the more basic one. I forgot to sort of include that one, but we'll just get rid of this one. Ignore that one's there or whatever. Well, you know what I can do actually quick here, easily enough, is I can just make it way less distracting. Just have it weighted out somewhat. Okay, so that's obviously the easiest one, right? The tangent method would give spots along here. So this is the idea that we're extending this to, is if I took a tangent slope there, it would give me this slope, this velocity value. If I took a tangent there, that's a terrible tangent. If I took a tangent, I'll use straight lines here that can make it easier. I can adjust it afterwards, but that would be a tangent very nicely to that spot right about there. And so that would give us that dot and so on, right? And so if you did a bunch of tangents, you get a bunch of spots, and if it forms a nice straight line, you're finding out that it is nice uniform acceleration, right? If your bunch of tangents led to this kind of graph, that would be obviously matching the idea of more and more steep. And so that would have again been, a tangent here is 0, so that's obvious. And then a tangent somewhere along there is here, and the tangent here might look like this, and so on, right? Just trying to get the idea. So basically, if you're seeing this kind of pattern as a result of your tangent values to that graph, okay, that we want you to be able to predict. So I'll spend a little more time on that one here, actually, because I do. This is something you need to be able to get comfortable with. So if I am, green line went. If I have a line like at a certain angle, let's say, just make it that angle, I don't have any choice as to where that thing touches the graph. When I bring it close to it, it touches there, right? So the tangent at that instant, right, gives me the velocity at that instant as well, and I could just move that dot to match with that one. Okay. So when you're putting a ruler against a page, it feels like there's way more, I don't know, vagueness to it, or whatever, because you can, like, against this, I can't do it on the smartboard because I have to pivot both ends at once. But really, like, it's pretty obvious on here. Like when I bring this line towards that graph, I have no control over where it touches, and that's your point of tangency. And then this slope gives you the slope of the line at that instant, which is your instantaneous velocity, right? So I hope that's starting to make sense. But when you do this in practice with a ruler, you'll feel like, you can sort of move the ruler back and forth a little bit to different angles, and it kind of looks decent. Just pick the best angle that sort of matches it. Okay. So if we were doing this here, I would put obviously a tangent here would be 0, and there would be something, and this one here, if I move it close, we have a tangent somewhere. This one was here. This one is here. Using blue by accident, right? That one is there, and this one could be anywhere in that interval there. and so on and so on, right? So we're going to have values from these that would be something like, this is going to be 0, obviously. Then whatever those other ones are shows you the kind of pattern. So whatever pattern comes out of a tangent process, if we got a tangent process that led to dots that look like this, then you should be able to look back to that original lesson where we were focusing on this a lot, where the smart car results were shown, little videos of the red and blue cars, whichever color you used. This would show this is a situation where we have it's slowing down. Is that right? Yeah, it's slowing down. No, it's speeding up, but less and less. Sorry, it's on a ramp, but it's less and less steep. So it's speeding up, and yeah, so it's speeding up because you can see here that we have this steepness, and then we have this steepness. So it's speeding up, but it's speeding up less and less because it's not going more and more on this graph. It's going less and less per second. Let's call it. So yeah, so just a reminder, what we're showing there is that you can have a DT graph that's curved like that could lead to a constant rate of change, or it could change more and more or less and less. Okay, so hopefully that's obvious to you now. So if you're taking a graph like this and making a bunch of tangent lines and graphing the dots, if you got a situation like this, you could say, oh, it's constant acceleration, uniform acceleration. Right? If you do a bunch of tangents and it turns out like this, then you're saying, oh, okay, well, it's speeding up more and more, and so on. Okay, so there's a lot of redundancy here. So if it turned out like this, then it would be accelerating less and less. Just the same results, same types of results I just went through. So let's try to carry one out here. I recommend you print this page and try these tangents yourself and see how close you get to what I do. So press pause and do tangents and get values and your tangent along the way. I'll do one with you here. So this, looking at it right now, we can answer some things. Is it uniform or non-uniform motion? Well, it's not uniform motion because it'd be a straight line, right? So it has to be non-uniform motion. There has to be some kind of acceleration, but we're not sure. So in the type of non-uniform motion, we don't know, right? So to answer this, we'd have to get the VT graph, okay? And so we do that, tangent by tangent as we go. And so this first one here, I'll walk you through. If you did a tangent, see how that touches that spot nice, then you'd have to measure, you'd have to read across on your graph, and this would be your final position of 0.4, initial position of 0.2. And so the displacement is the 0.4 take away the 0.2. The displacement was 0.2. The time numbers go way down to the bottom here. The time numbers, it's a little hard to read the scale here, but if you look at changing by 0.2 in steps of 4 steps, so each step is 0.05. So this is 0.4, 0.45, 0.5, 0.55, and so on, right? Yeah. So 0.5, 0.45, 0.5, 0.55, 0.6. I just said wrong words there for some reason. But yeah, so you can approximate the numbers nicely, right? And so this point here in the end, we can approximate what those are. So I have it listed as 0.94, take away 0.46, based on that being a little past the 0.45 mark, this one here, right? But anyways, we get a time interval, and then you just do the slope. So you do the 0.2 divided by the time interval, and you get a value for the slope, which is 0.42, and then you graph it on the, you just graph that on the thing. That's your velocity. That's in meters per second. And so you graph it at 0.42, which would be somewhere around here, right? Again, do the same thing here. We got a scale of 0.2. It's the same kind of scale, actually, right? So 0.42 is just really, really 0.4 number. So that dot there should be where you get your tangent. If your mark, if you make your tangent to that time interval of 0.6 seconds, and so on and so on, right? So the possible results for the curvature, it could be a nice straight line, it could be a curve up, or it could be a curve down. You just need to do a bunch of tangents to figure it out, okay? So again, I recommend you try that because it's something I'm going to ask you to do. This is the result. So on this one here, if I pull this little transparency over here, I can actually line it up like that. So you can see, the computer generated VT graph goes right through that manually slope, of a tangent calculated velocity. So there's the 0 at the beginning, and there's the result. So basically, if you did a tangent in this spot, you're going to get a value of about this amount, and you put the dot on. It should all match up nice, right? So obviously, that's the same thing there. The next step to look at here would be to talk about acceleration. And I'm a little bit ahead of myself here, but I mean, like, it's something I want you to be able to think about in part of the homework. So for acceleration, talking about the change in velocity, right? So this is very much representing since this is a uniform acceleration question here, we can say that this is a delta v over a delta t, in which case acceleration, okay, the a with a vector, acceleration equals delta v over delta t. And so you can actually get the slope of that line and say what the acceleration is. And I just feel like I should maybe make my triangle there a little bit better. It should be fairly vertical, but hard on the smart board here, close up. A big screen like that, that looks a bit better, right? So you can actually measure slope on a VT graph to get acceleration, and I'll ask you to do that in part of the assignment tonight. So I just did it on this page here, so skip that one. So if you're interpreting this, just going back to the original stuff we started talking about, you should interpret this as uniform motion, constant motion, right? And then stopped for a while here, so uniform motion of 0, really. And then this section here, we're going to start to go backwards, and we're going, a slope of slow to faster to faster to faster. So this one is non-uniform motion because we're changing, and it's negative in the negative direction, like I said, because your slope is, you're going from large numbers to smaller numbers, and your slope is in the negative direction from math class even. So the velocity is changing more and more and more, obviously, because we're going to steeper and steeper slopes, right? So it might look like something like this, where it's at a set value, this number, and then it's at 0 for a while, and then it is either changing constantly or changing less and less or more and more, right? That should be stuff that you should be able to do at this point. I showed here the idea of, like, is it changing instantly? No. So maybe it's changing where it's more and more or less and less or something like that, right in there. And that's it for the lesson part of it. So I'm going to ask you to do tangents, lots of tangents on this. So maybe you're going to do tangents in, all sorts of spots. So you do a tangent here. Let's make a tangent like that. So that would be a good tangent to that dot right there. So I'll just put a dot on there, like about there. Then I wanted a tangent to spot A here, or any spot really. This is just for getting the velocities, but the ABC, I'm asking you to talk about the acceleration. So once you have your VT graph, then do the slopes at the ABC spot. So there's no reason for me to have to stick to that spot. So if you print this out, this will actually be good tangents for those spots for sure. So that looks like it's about right there. And then I'll let you just do the rest of them. But that slope is just going to be entered in as a value along here somewhere. So it might be like that, but I'll have to erase that because I'll get you to put it where it really is, of course. So that's just your tangent slope method to get VT graphs. And so you'll get a VT graph result here, and you can describe the kind of motion. And it's told, yeah, you know what? I modified this recently and added in this uniformly accelerated motion. So you'll be looking for it to be a straight line. So should be a straight line. So if you're doing your tangents and your calculations, right, should be a nice straight line. And then, yeah, when you're analyzing it, you can answer what you think the accelerations are at these points. Okay. Should point out that this is a cart that's going up a ramp. Okay, so maybe you should think about this in advance too. This is the graph we saw before, where we push a cart up a ramp and it starts with a velocity, slows down, and it goes down to a velocity of 0 at the top, and then it speeds up back down. Okay, so this is a cart, right, going up a ramp, stopping, and coming back down. So I could say going up a ramp, slowing down and stopping, and coming back down. So that's what it is. So based on that, even I think it'd be good for you to like answer what you think the acceleration is at points A, B, and C. This is at the top, right? And then A, B, or A and C are just on the way up and on the way down. So I'd like you to definitely say what you think. Run your page when you're submitting it, like what your first thought is about what the accelerations are. And then when you see your results here for your VT graph, analyze whether you think you're right still or if you need to change your mind. This is a bit of a misleading, spoiler alert, right? It's a bit of a misleading type of situation. And we need to get it out of the way that we need to fix that, basically, that misleading nature of this. All right, so these are pretty straightforward, just analyzing this. You can sketch a velocity time graph for this thing. So it'd be nice actually if it was right underneath it, but you could just make a VT graph. I guess I could switch this because you're just going to print it from here anyways, right? Let me just move that down. Give you room to do a VT graph right underneath this one. You can put an appropriate scale on there. So I'll just make it like that so you have all sorts of options. That'll work. And this one here, redraw. Do a VT graph of that one. So I'll put a room underneath this to do it yourself, but I'll just show it here. And make a scale. And then these ones here, just it says draw conclusions about the acceleration of the motion represented. So this is related to this classic kind of 3 possible results situation. So hopefully you find those pretty easy to do. This is the one where you're doing tangents. This one you're just calculating like slopes of straight lines and drawing very simple VT graphs. So this is the more challenging page for sure. So you just have to try and get comfortable with the idea of drawing tangents and trusting the result you measure for the associated, property that's to do with it, right? So in this case, it gives you the velocity in an instant. All right, so that is it for me. Thanks for watching, and I'll see you next time.